Hello everyone. Today we're going to learn how to represent graphs using an adjacency matrix. So learning how to do this and understanding how to do this is actually a very crucial concept in graph theory because it's going to help us solve problems that are related to network, connectivity, and paths, and also has some good practical applications in the field of computer science and computer engineering and sorts of other fields related to it. So why don't we dive right into it? Let's get started. So we are given, it's actually our first activity. We were given a couple of things. We got a map and we got the order by which the vertices in our map should be. Okay, actually, this is actually four, I think. So let me correct that one. So we were given a map. Okay, let me just zoom in. So we have a map here, which is also going to stand as our directed graph. It's a directed graph because you can see, the arrows pointing from one location pin to another. Okay, that's what you call an edge. Actually, that is called an edge, right? The arrows you're seeing are edges and the location pins, right, are vertices, or each one is called a vertex. Sometimes they are called as nodes, but in this case, we're going to call them as vertex or vertices. And the arrows here are also sometimes called as links, but this time, we're just going to call them as edges. Simple as that. So remember these terms. It's going to be very helpful for us later on. So as you can see, we don't really have an idea which of these vertices comes first. So let's go back to our info here. So I think what we can do is indicate the numbers on our graph. Why don't we do that? So Del Nacia for Park is our first vertex, which is right here. The second vertex is the San Pedro 6 covered court, which is this one, okay? And Nia Village is our third vertex. Our fourth one is San Pedro V Park, okay? Let's just make it a little bit bigger, right? Four. Okay, so what about Napocor Village covered courts? That's actually number nine. So we got nine, almost at the center of the graph. Napocor Village is fifth. Vertex 5, Zytec Chapel is vertex number 8, Himlayang Filipino is our 7, and Maria Luisa Townhomes is our 6th. Okay, so let's zoom it down. There you go. All right, we have indicated the order by which our vertices are organized. So I think we're ready to build our adjacency matrix now. But first, let's create a table. Since we have 9 vertices here, we're going to create a 9 by 9 matrix. All right, let's continue by building a table first. Let's make a table that will help us build our adjacency matrix. So we got 9 vertices. So that gives us 9 columns and 9 rows. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then horizontal or vertically we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's fast forward this. I'm just gonna continue, but I'll do it in fast forward. There you have it. We now have a table for us to fill in with zeros and ones. Okay, so now that we have our table created, I think we are now ready to populate our adjacency matrix. So one thing about adjacency matrix is that we need to use zeros and ones to check if there is an adjacency between vertices. So that's what we are going to do. And in order for us to understand, I have here a sort of a formula to help to guide us along the way. So an entry of the adjacency matrix A, we call A, between the ith row. So let's call the rows as I, and J as the columns. So an entry from the adjacency matrix of the ith and the jth column will be 1 is equal to 1 if ij is an element of the edge set of the graph it's representing. In this case, it's called, I just call it graph G. You can call it by any other name, but as long as it's the graph that the adjacency matrix is representing. So, in other words, it's 1 if there is an adjacency or an edge being indicated in the graph. Otherwise, we indicate it as 0, right? If there's no adjacency or no edge, right, then that is just a 0. So let's check our directed graph against our adjacency matrix. So we do it by first checking the row against the column. So our first row is row number 1, which is represented by the vertex 1 going to 1. So is there any edges going back to 1? I guess not, so it's just put 0. In other cases, there are actually, so, but that is not visible in our graph. Sometimes you'll see a loop, right, from the vertex going back to itself. That is actually considered as a 1. But in this case, we don't have it, so 1, row 1, column 1 will be 0. What about 1 and 2? Let's check. 1 and 2 actually has an edge going to from 1 to number 2. So let's indicate that as 1, right? I will write the color. That's 1. And then 1 and 3, that is a 0. 1 and 4, that's also a 0. 1 and 5 is a 0. 1 and 6 is a 0. 1 and 7 is a 0. 1 and 8 is actually a 0. 1 and 9 is also a 0. So, right, I think you're just gonna get the hang of doing this as you go along. So let's go check row number 2. 2 going to number 3. There is actually an edge, so let's indicate that as a 1. And, oh no, sorry. Let's check 2 going to 1. So 2 going to 1, no. So that's a 0. 2 going to 2 doesn't have a loop itself, so that's a 0. 2 going to 3, there is 1, so we got 1. So 2 going to 4, no, that's a 0. That is a 0. 2 going to 3, oh, 2 going to 5, that's 0. Okay, 2 going to 5, that's 0. And then 2 going to 6, that's 0. Alright, 2 going to 7, 0. 2 going to 8, that's 0. 2 going to 9, that's also, actually, that is a 1. Alright, see? So, actually have another 1. Let's go to row number 3. 3 going to itself, going to 1. Sorry, 3 going to 1 is 0. And 3 going to 2 is actually 0 because the arrow is in the opposite direction. And 3 going to 4 is 3 going to itself, that's a 0. 3 going to 4 is also 0. 3 going to 5, 0. Don't see anything else going, alright? Going for connecting to 3. How about number 4? Row 4 or the vertex number 4, let's check. So 4 going to 1, that's 0. 4 going to 2, that is a 0. 4 going to 3, that's also 0. 4 going to 4 to itself, that's 0. 4 going to 5, there's actually 1. It's actually an edge. 4 going to 6, that's 0. 4 going to 7, there is 1. 4 going to 8, there is 1 too. 4 going to 9, no, that's 0 because the arrow is pointing to the opposite direction. Let's go to row number 5. 5, 1, 0. 5, 2, 0. 5, 3, 0. 5, 4 is also 0. 5, 5 is 0. 5, so we have 5, 5, 5, 6, 0. 5, 7, 0. 5, 8 is 0. 5 and 9 is also 0. Let's go to 6th row. 6. 6 and 1 is a 0. 6 and 2 is also a 0. 6 and 3, 6, 4, 5, 6, 7, 8, and 9. And all zeros. 7, let's check 7 and 1, that's 0. 7 and 2, that's 0. 7 and 3, 0, 0. 4, 7 and 4, that's in the opposite direction. 7 and 5 is 0. 7 and 6, there actually is 1, so that's 1. 7 and 7, 0. 7 and 8, that is 0. 7 and 9, that's 0. Let's go to row 8. 8th row, let's check 8. 8 and 1, no, that's a 0. 8 and 2, that's 0. 8 and 3 is also 0. 8 and 4 is actually 0. It's in the opposite direction. 8 and 5 is also 0. 8 and 6 is also 0. 8 and 7 is 0. 8 and 9 is 0, 0. How about 9? 9 is actually almost right at the center. So let's check. 9 and 1 is 0. 9 and 2, that's the opposite direction, 0. 9 and 3, 0. 9 and 4, there is 1. Right? 9 and 5, that's 0. 9 and 6, that's 0. 9 and 5, 9 and 7, that's 0. 9 and 8, that is 0. And 9, going back to itself, that's 0. There you go. We have completed our adjacency matrix. So we have a couple of ones, but we have a lot of zeros. But there you have it. That is how we can represent our directed graph using an adjacency matrix. Hi everyone, welcome to this video where we'll explore probability in the context of discrete mathematics. Well, probability is a key topic in discrete math, and it helps us understand the likelihood of events in systems with a finite set of possible outcomes, such as, tossing a coin, rolling a die, or drawing a card from a deck. So let's break down how probability applies to these classic examples, and let's find out why understanding them is fundamental in discrete math. Well, in discrete mathematics, probability allows us to measure how likely an event is to happen within a finite set of possible outcomes, or a discrete sample space. We represent probability as a number between 0 and 1. An event that turns out to have a 0 probability means that it has a 0 chance of happening, or that is impossible for that event to happen. Well, an event that has a probability of 1 means that it has 100% certainty that it's going to happen, or it's guaranteed to occur. And the formula for calculating probability goes like this. P, enclosed in parentheses, we have E, which stands for events, right? It's the event that is one that you'd like to calculate the probability of. So P of an event is equivalent to number of favorable outcomes over the number of total possible outcomes. This formula works perfectly in discrete structures because we're dealing with countable and distinct elements here. Alright, so let's start by working with our first event. So in this first event, we're going to calculate the probability of the probabilities in tossing a coin. So there are actually two possible outcomes in tossing a coin. So let's have a quick look at our coin. So as you can see, I'm showing here an image of the two sides of a coin. This is a fair coin. So there are two sides. So the first side is called as, let's call it head, and the second side of the coin is called as head, as tails. Now the origin of this is, of calling it tails, is actually from, not really from a quarter, from a quarter of a dollar, but just for a fun fact, the origin of the heads and tails actually goes way back to Greece, ancient Greece, where there is a coin that depicts Athena. On the other side is a sacred animal, which is an owl. So that's why I think even from long, long way back, they already have this kind of concept that one side of the coin is the heads, one side of the coin is called tails. Tails. But it still applies to, still works with the quarter because the other side shows an eagle, which is an animal with a tail. And on the other side is a head of a person, or in this case, the president of America. So going back to the probability um, of getting a heads or a tail, that's going to leave us with two possible outcomes. One and then two is the tails. So total number of possible outcomes would be total number of possible outcomes. Sorry if I just spelled it right. Outcomes is equal to 2, right? And then what about getting a heads or a tails? Getting either a heads or a tails would, we can say, would be called as a favorable outcome, right? So let's say, for example, we're trying to get a heads, right? So the favorable outcome for us, which means if we're going to bet on getting heads, that's, if we get heads, that would be favorable for us. We're going to win the bet. So we call it number of favorable outcomes. In this case, getting ahead is just one, right? The same goes if you're wanting or trying to get the tails, right? So you also have one favorable outcome doing that. So these two information are very important for us in calculating the probability of either getting a heads or a tails. So why? Because actually the formula for probability goes like this. So we call it the probability as P, and then enclosed in parentheses, we can actually put there the name of the event. It could be just a letter, it could be a character, it could also be a name that you can put. So in this case, we just added E for the event is actually equivalent to number of favorable outcomes over, okay, so over the total number of possible outcomes. So in discrete structure or discrete math, we have two favorable discrete outcomes, right, over the total number of possible discrete outcomes as well. So this also relates to the sample space that we have. We actually have a heads or a tail. So our sample space would be related to that. Sample space is actually a set, right? Or we can just say, you can write it as a set of all the possible outcomes. In this case, we get one H for heads and tails. So we only got two. So let's calculate the probability of getting either a heads or a tail. In this case, we said earlier, we want to get the heads. So let's use that. P, and then we replace it with H, since we're looking for the heads. And how many favorable, what's the number of favorable outcomes of getting a head? We only got one. And how many possible outcomes do we have in total? We have two. So we're going to end up with, right, 0.5 chances, or if we turn it into a percentage, that's going to give us 50%. So that means you get a 50% chance of getting a heads when you toss a coin. And this also applies if you calculate for the probability of getting tails. So I think the same formula goes 1 over 2 is equal to 50%. getting a tail. So there you go. That introduces us uh, as to how to calculate probabilities of tossing a coin. All right, so now let's go to our second part. This time, we're going to calculate the probability of rolling a die. So let's have a look at our illustration here. So as we know, a fair die, if we say we use the word fair die, that means our die has six faces. So here's a three-dimensional representation, but each of these faces represent a number. So phase 1, phase 2, 3, 4, 5, and 6. So there you go. We have six faces. So in order for us to calculate the probability of rolling, the calculate getting a number out of rolling a die, we need to use the formula of calculating probability. So as we know earlier, the formula goes by P, the name of the event, is equal to the number of favorable outcomes over, sorry, that's hard to do now. Okay, sorry about that. All right, over straight line, total number of possible outcomes. Okay, there you go. So now we have that formula. We can actually substitute the information that we have about rolling a die. Say, for example, let's choose a different color this time for, yeah, to make it easier. So for example, if we're rolling a die, we calculate the probability of getting, say, number 4. Let's say the event is called 4 because it's all about getting number 4. The number of favorable outcomes that we have is actually just 1, right? Because there's only one 4 in this set of possible outcomes. So we can write there 4 over how many possible outcomes do we have in total? We have 6. So we end up with 4 divided by 6. If we reduce it further, we can divide both the numerator and the denominator by 2. So that's 2/3. So 2/3 is going to give us 1.666. That's going to be a repeating 6 digits. So we can just say, let's reduce it to 2 decimal places. So we're going to end up with 1.67, or if we turn that into a percentage, we multiply it by 100, that's gonna give us 16.7%. So that is the probability of us getting a 4 when rolling a die. Alright, so now we are on the third part of our activity. So we're going to find out the probability of drawing a card from a deck. All right. So what we are working with is actually a standard deck of playing cards. So what information do we get about that? So that means if we're working with a standard deck of playing cards, that means we have 52 cards in total. Or maybe I should write it over here. 52 cards. Okay, that's all the cards that you have in a standard deck of cards. That is to say, we don't have the jokers in that. So we're not gonna consider that in calculating the probability of drawing a card from a deck. So what else do we know about a standard deck of playing cards? What we know is that there are actually four suits, right? We got one, clubs, diamonds, hearts, and spades. So that means we have four suits in a deck of cards. Let's erase that part. Erase that one. And what else do we know? We also know four suits, right? So we also know that each suit contains how many? 13 cards per suit. Okay, so let's see what we can utilize in order for us to calculate the probability of drawing a card from a deck. So let's say for example, we are going to draw an ace card. Okay, an ace card. So what is an ace card? An ace card is the one that's labeled A. So these are the ace cards. One, two, this one. Actually, it's this one, and this one. So what do we know about the ace cards? There are actually four ace cards in our standard deck. Four cards. Since there are four suits, right? So each card has a different suit. The club, and we have the ace of clubs, we have ace of diamonds. Here we have ace of hearts, and we have the ace of spades. So why don't we apply the probability formula in order for us to calculate the probability of getting a card from a deck since we now know these information. So let's organize everything. Okay, probably turn these off first. Then this one, I could probably erase this one. Okay, so let's go back to our formula earlier. So the probability of an ace, let's call it an ace, right? Of getting an ace from a deck of cards is the favorable outcome. So what can we say would be the favorable outcomes? Number of favorable outcomes over number of total possible outcomes. Outcomes. Sorry, let's spell that correctly. Outcomes. So let's go back to the information we got earlier. We actually have how many favorable outcomes do we have? Since in a standard deck of 52 cards, there are four aces. So we can write four over here. All right, since there are four aces, so we got four favorable outcomes. And then how many possible outcomes do we have? So we're working with 52 cards here. So it can actually write 52. So there you have it. We now have a formula to give us a probability of drawing an ace card. So let's actually solve it. Let's go for it. 4 over 52. And that is, if you're going to calculate it, that's going to give us, actually, if we can still reduce it, if we divide it by 4, we can reduce it to 1 over 13. Okay, so P, why don't we push it over here? So 1 over 13 is actually equivalent to 0.077, or we can just say it's a 7.7% chance. Right? So we have a 7.7 chance or probability of drawing a card of chance of drawing an ace card, an ace from a deck of cards. There you have it. So I think this knowledge is pretty helpful for us if we're going to learn how to calculate the probabilities of events that occur around us. So that's it. Thank you so much.